Good morning. Happy Saturday. This morning I got a coffee mug from Gary, who hides in the back over there, that says "Free Thought Matters." And I think that is as good of an introduction to Science on Saturday as anything. Welcome to Free Thought Matters Science on Saturday. And of course, we timed it so that whatever snow and ice and rain will happen after everybody gets home today. Before we get started, a couple of housekeeping things. Um, First of all, they were gone by like the earliest ever, so congratulations. I'm like, where? I always go for, by the time I get here, I figure there's like one bagel left for me. Nope, not a donut. No, there's no coffee for my mug. There's nothing. How do we fix that? I think there's only we want to make sure we just keep on ordering more and more and more and more, and we're going to find that final limit where number of people at Science on Saturday equals number of donuts and coffee. If someone wants to model that, I'm happy to see. We'll do a talk on it. Couple of housekeeping things real quick before we get to this. So today is the last lecture here. So next week is our normal scheduled high school science bowl. We always take a break every year for high school science bowl. You are all invited to come if you want. There are 32 teams, Dee Dee? 32? 32 high school teams coming to compete in a science competition, a quiz competition. Every year they get smarter and smarter and smarter. And I think that means we know, like slower and slower and slower. It's really remarkable. It's a round robin. It's our equivalent of March Madness, and anybody and everybody is welcome to attend. So that's next Saturday. Now, we'll have this stuff up on the website. I see some people taking photographs, right? But we'll also have this up on the website. So the March 1st, 8th, and 15th lectures will all be here. Right, so this is Prospect, and for those of you who know Princeton, out over here is Harrison Street, and Washington is over here, right? But we'll have all of this up on the website. You're going to park right here in the Prospect Avenue garage, and then there'll be signage, and you can see to walk right over, and it's not very far, over to Mater Hall. So the website will reflect that. We'll have GPS coordinates, everything else you need. There'll be signage, and really the trick will be just making your way. And like I said, this is just this one building over here, and then we're right over there. Here's a picture of it. So we're upgrading the seats. That part's clear. The only thing is Princeton University's rules, but no food or drink will be allowed inside the auditorium. There's a lobby, not as big as this one here, but there's a lobby, and we'll have the bagels and the donuts and the coffee out there, but we will have to ask that you don't bring it inside. And for the folks listening on Zoom right now, no changes, right? We will be broadcasting as always from there. Any questions? Yeah. Overflow. Overflow in terms of if there aren't enough seats. So at least right now, we've sort of taken how many people have come every single lecture. We're good, right? There should be enough seats. But, Dee Dee, just in case, so just so everyone can hear, just in case, we'll broadcast into another room in Mater Hall. Yeah, so the entrance to the parking garage is off of Prospect, and you can see it right here. I mean, well, in the map, but yes. No? Oh, wait, hold on. Hey, Dee, why they let me do this is really unclear. Every single question is, Dee Dee. Hold on for 1 second. Now you know the secret behind everything.
Okay, can I borrow this thingy? So Andrew mentioned before, where's the light? Is it this one? Okay, he mentioned before, this is the garage where we're all going to park. However, what we're going to do is put signage up so that you are able to come out of the garage onto regular streets and walk down Prospect up to Olden because this pathway here isn't very accessible. There's steps, there's trees, there's uneven sidewalks, so it's better to just go all the way around from one corner to the other to get into Mater Hall.
Garage. Isn't it right off the top?
It's got a couple of entrance. It's right here. This is the entrance of the garage.
This is the only one I know. This is it, right? So you're on Prospect, you hit it from Harrison or Washington or wherever you got to it, and then it's pretty obvious. It's this, and you come in right here. I see the people who have been in this garage before nodding their heads. But we will have signage up. Oops, that was me. We'll have signage up everywhere for March 1st. And then once you do it once, obviously, it'll be much easier. Right? And so then we're going to do quantum computing, the brain, and polling. That's the one that we had to move to the end. Those will be the 3 lectures for the March ones. Any further questions of something I have also mostly mangled and butchered? So the question was about touring, right? So the answer to that is we're in a very unique position right now as we're finishing buttoning up the National Spherical Torus Experiment upgrade. And so we are still offering tours, but they're quite limited. And so if you do want to take a tour, then go to the website and go to the sign up for the normal public tours. But we've had to limit the number of tours that we offer this year just because we're very close to putting everything back together. Dee Dee? We're not doing a tour this year for science. Right. So we normally have done that in the past, and so that's just a legacy thing that we should have gotten rid of. So no tour. For the tour? I mean, it's locked up right now, but you could walk over. Okay. So with that, finally, anybody raise their hand if they are not currently using a lithium battery? Right, of course not. So it is my pleasure to introduce the Science on Saturday, Chao Yan, the founder and CEO of Princeton NuEnergy. You should be on.
Thank you. Thank you so much for the introduction.
And can we hear him in the back?
Is that okay? The voice? Okay, thank
Yep.
you.
Excellent. All right. Well, welcome. There is his bio, but we're going to hear something that I've been very excited to hear about, which is what are we doing about the fact that every single one of us has a phone in our pocket, we use a computer, drive electric cars, everything else. So I've been looking forward to this talk for quite some time. But before we get there, I have to ask you 3 questions, important questions. Tell us about when did you first get interested in science?
I don't remember. Maybe around 9 or 10 years old in the elementary school. I think the teacher showed us something. I think the one thing I remember is I still remember is the teacher show me a crab and hit it and the color turned to the red. I think that is a very early time I remember there's something called science. So yeah, it's that time.
Excellent. So then you mentioned a teacher, but tell us about a teacher anytime from being a little kid on up through your graduate work that had an influence on you.
Yeah, I think the most important person to me for science, I think, is my PhD advisor. So sorry I didn't mention my postdoc advisor and also my elementary school teacher because I think my PhD advisor, he focused on the one single research topic for his entire life. It's like a high pressure kinetics. So I think not many people work on that in the United States, in the world. I know almost all the professors in that field. So we work on the high pressure, which 100 bar, 100 atmosphere pressure, and just for single elementary reactions, OH plus OH for a long time. So it's really make me feel I did something work really, really useful. So it's really important to me. So I spent 5 years with him, very, very important to me.
Love that. Last thing, something when you're not working on your research or trying to continue to recycle lithium, what's something you do for fun?
Have many hobbies. I just came back from Deer Park, Utah, actually this morning. So I sent my kids to there to ski. So this is my recently maybe 7 years hobby, which is ski with my kids. So last night I warning them, tell them you can only go to the green line without me. So they are very unhappy right now. They said they want to go to blue. I said wait for me.
Well, thank you for coming back for this. Anthony, we could switch it over, but Science on Saturday, PNE's role in the life cycle of lithium-ion batteries. Welcome and thank you.
Thank you. Let me share the screen first. So this is okay. Share to make sure everyone can see that. Okay, so appreciate for the introduction. And I actually spent 4 years in Princeton, exactly in that location, where's the next presentation in the following weeks. So I'm very familiar with the E-Quad, so I'm very familiar with where's the garage, where's the entrance. So, so they used to call the North Garage, but right now they changed to Perspective Garage. So anyway, but this is my first time in PPPL. And I'm pretty nervous, to be honest, because I know a lot of the good research here, and I'm not sure I'm qualified to give this presentation here until they told me, okay, this is for high school students. And but this morning when I come to here, I'm really looking for high school students. and I just double confirm, triple confirm with them that it's fine. It's really for that. Also, I say okay. And if this is not too depth for the science, and I talked to my colleagues, Dr. Chao Yan, and is also the CTO and also co-founder for the company to join with me together today. And he spent very long time in Princeton University and also PPPL. And my other co-founder, Dr. Bruce Chao and Dr. Yi Guangzhu, they also spend time in PPPL and in Princeton. So if there's more tech questions, Dr. Chao Yan can help to answer that question. And just let you know the reason why I'm not so confident, because my research is not only focused on plasma. I spent 5 years on the high pressure kinetics. And later on, I spent a few years on combustion and low temperature combustion, high temperature combustion, all kinds of combustion. And then work with Dr. Chao Yan, Dr. Bruce Chao, and work on more materials and also plasma technologies. But yeah, let's move on. So there's a one-page introduction for the company. So starting from 2019, we found this company and spin out from Princeton. And we think we have a great technology to recycle batteries, particularly using plasma to handle the battery materials. So you can also use it to recycle battery materials and also to synthesize new materials. So initially, we have our R&D technology development from very small plasma tube to actually pretty big plasma tube. We call the lab scale. So in that one, we have a support from university, from the DOE SBR program. And that is for the first, I would say, a year and a half, something like that. And after that, in the middle stage, the demonstration stage, we continue to get more grant from the Department of Energy, the ERE grant, the MTO grant, and some other grant, and also supported by New Jersey government, NJ, EDA, and CSIT. So this help us to give the larger lab scale and also more like a automatic the control everything, not only the plasma tube. So this is the foundation to the next step. So the next step is more moving to the commercial stage. So we were actively looked for partners. So the first partner, very important to us, called Wistron. So probably in the middle, you can see the Wistron. Wistron is a Taiwanese company. They are very large, the consumer electronic devices OEM. So their obligation not only to make the electronics, but also recycle. So in Dallas, Texas, they have a large site to recycle electronics. So then they naturally have a lot of battery want to recycle at that time. So then we work together and build a pilot line there to recycle batteries. So the pilot line is already not in the looks like a lab scale stuff. Is everything is industrial standard, like a UR certifications, how you handle the water, how you handle the waste gas. That is all need to take care of. So that is a very important foundation to move to larger commercial scale. And actually, this is the most important and also most difficult part in the United States, because most investors, they do not want to invest into this stage because they need to invest a lot, but a lot of risk. So that's why we think this is very important, and we get a good partner to work with us in order to build this the plant. So the demonstration has been run over a year and a half right now. So we demonstrate we can recycle the electronic devices batteries, which is the small batteries, and also EV batteries, and also manufacturing scraps. And then after that, we are building the next one right now, the full commercial scale, the one in South Carolina. So with many other investors. And the good thing is that we have a site over there, and also we get all the permit, we get local support, and that is very complicated, but we have a great team to work on that. So the phase one, we starting to handling the manufacturing scrap. The equipment right now is in installation. So hopefully in the future, 2 to 3 months, it can start commissioning. And that is a brief background for the company. In the past 5, almost 6 years, we did a lot of work, and we have another colleague, Janet. You want to raise your hand here? And she is helping us to the government affairs, helping us to help to communicate with all the states, which is very difficult. Trust me, very difficult. I cannot handle that. Yeah. Okay, so moving to the more background information. So this slides actually I'm very familiar with. And before I step into the battery, because as mentioned, I used to work in the combustion research. So in the United States, actually, the renewable energy is a small portion. The major portion is still the natural gas, and also the oil, and some is nuclear and also coal. So we're focusing on more about the renewable energies. So that's what we want to focusing on. And particularly, we are focused on something about the batteries. So we're going to move into there. But you can look at in the US right now, still major is not the renewable energy. Unfortunately, I don't know what's going to happen, but we hope this can increase in the future. So this is how we spend those energies. Basically, the left-hand side, which is a source of the energy, and the right-hand side is where we use it. Actually, you can see the transportation is the largest one in the United States, and the transportation definitely heavily involved with the battery, which is the electrical vehicle right now. No matter it's a small car, large car, trucks, everything. So this will be one of the trend. And there's industrial usage. This part is is also important. So just want to give you this two big part. Where's the energy come from? Where we spend energy in the United States. And this is want to let you know the electricity supply and demand. So the electricity is not basically steady stage. They always up and down daily shift. So that is why right now you can see a lot of the energy storage system people are thinking about. So because of this wave, you want to store more energy when you have when your supply go to the peak, and then use it with demand go to the peak. So that is what we want to do. And then the traditional like a hydro storage and some other storage, but I think in the future the battery storage will become most important thing. So this is what we want to show here. So basically, you can see the storage system before 2018. So the majority is the pumped hydro, become the majority storage, and others, basically thermal storage and a battery storage, looks like it's a small portion. And I mean, so this is only 6%. And the battery is about half of the storage. But this number is for 2018. But if you see the next one, if you can see for the future couple of years, so 2018 is only a very, very small portion. So you can see this gonna growing very, very fast. So we think is that this might growing even faster because of the demand for like a large data center, and so a lot of demand is increased. So that's why you can see the 20 right now is already operating. The number is much larger than 2018. The major growth is for batteries, and the plan is even more. Okay, this is the other we want to mention is that for the transportation and also energy storage, which give you a big demand for the materials. So basically, no matter what you want to do, transportation or storage, you need to have materials to make the new batteries. Very unfortunately, in the United States, we only have very little supply. You can see this is a forecast for 2030. Basically, we can supply roughly about 60,000 tons per year, but the demand, you can see, is 130 million tons per year. So we have a huge gap in order to supply the materials. So that is one reason we want to recycle the batteries and use the materials and reuse them. Okay, so then we go into battery, lithium-ion battery supply chain. So probably you already know this, but I want to give you from beginning to the end. So for the first step for the supply chain is mining. So we need to mine all the materials to use them. Like a majority is nickel, cobalt, lithium. So cobalt majority is in Congo. Nickel in many regions, but right now most of the popular is from Indonesia, Australia, and some other. Lithium actually from Australia a lot, and a lot of place. But this is a mining, you can mine all these materials and to use. And very unfortunately, those materials very little mine from United States or North America, and very little we can process here. That's very important. So after you get the materials, you want to process these materials with like a refining process, and you want to get the pure the metal to use. And after you get the pure metal, you want to continue to synthesize precursor. We call the materials need to build the cathode active materials. And I didn't show the number here, but roughly about the precursor. Maybe 90% capacity is outside United States. I would say only in Asia, maybe 90 to 95%. So we have very little capacity here. And also the anode part, which is graphite, we also have very little capacity we can handle here. So after you get all the materials, which is the foundation, and then you're trying to assembling everything to the battery. I'm gonna show how battery looks like in the following slides. But you assemble all this cathode, anode, and the electrolyte and memory. You make them together, make a battery. So we do have a couple of the cell manufacturers in the United States, like Panasonic, LG, Samsung, SK, and so on. So we do have some capacity to make batteries. So more bottleneck is materials. So after these two, you move into the application part. So you want to you get each cell, each battery cell. In the iPhone, in the phone, but just one cell. But in most like an EV, there's 1,000 cells. You want to put the cells into the module, like each module maybe have 50 cells, and maybe 10 or 20 modules make one battery pack. So this will make the pack, and then you put into the electrical vehicles, and you can drive it, or you put the energy storage system. You can use it for maybe 20 years, 15 to 20 years. But at the end, we want to show is how you handle and as a waste. So our responsibility is to handle this end of life recycling or reuse. We're focusing on more about recycling. Reuse is the other topic we touch a little bit. Reuse is very interesting, but the challenge for reuse is how to make sure all the old batteries are standard. So very difficult to make it a standard, and also safety is very difficult to control. But we focus on more with recycling. All right, so this is really for high school student, how the battery works. So we have a cathode side and anode side, and cathode side, which is we put the aluminum foil, and you put the cathode active materials powder paste at the surface. So this example, which is NCM, lithium, nickel, cobalt, magnesium. So NCM materials. The anode side, which is you put a copper foil, and then you put the graphite, paste the graphite on the surface of copper foil. So you make the two electrode, and then in the between is a separator. It's a kind of like a plastic, but the separator. So it's make sure the cathode anode won't touch each other to become short. So then you put electrolyte inside. So people always call the wet battery because you have electrolyte inside. And there's other concepts called a solid state battery, which is dry, means the electrolyte is not the liquid anymore. But the normal lithium battery right now, electrolyte is the liquid to make sure the lithium ion can flow inside from one side to each other, from to the other side. Okay, so this is when you discharge the when you charge the battery. Basically, this electron go from one side to the other side, can use the electron, and then there are some reactions happening here. You can see the basically the lithium plus electron and plus NCM, and on the other side, the lithium go from cathode side to the anode side internally, and then lithium can stored in the graphite. And then what is the discharge? Basically, you can see it's going to be reverse. Okay. So this is how reverse. So basically, the lithium is very important to transfer from one side to the other side and make the electron can go outside. So this is how basically the battery works. And then moving to the next step is we want to show what is the major type of the lithium-ion batteries. Actually, for the different application using different materials. So there's 5 major one right now on the market. From the top, LFP, lithium iron phosphate. So NCM, nickel, magnesium, cobalt. NCA is nickel, cobalt, aluminum. LMO is lithium magnesium oxide. LCO is lithium cobalt oxide. So we have a different application I'm gonna show to you very soon. Before that, I'm gonna show they have a different, basically, advantage from different materials. So for the LFP, this materials on the top, which is very safe. This is a very safe materials and have a longer lifetime. However, the energy density is a problem. So that's why in the US, majority EV is not using for LFP because of the energy density. So the US customer really want the long range, the EV. So that's why in the US, we use NCM most. But in China, or some other region, particularly in China, most EV is made by LFP because the cost is really low and also it's really safe. This is for the LFP and also for the energy storage because people don't care about energy density. They can have a larger space for the energy storage. So that's why most energy storage using LFP materials as well. On the next one is NCM. So yeah, NCM, hope you can see it. NCM is a very high energy density materials. You can see, basically we show there, if you can see, maybe I can ping there a little bit. So from here, so you can see it's very high energy density. So that's why most EV in the US using these materials. The challenge that this material is more expensive because obviously cobalt, nickel are more expensive than phosphate, iron phosphate. And also lifetime, you can charge maybe few thousand times, but not going to 10,000 times or even more. And also safety is a little bit the challenge for these materials. You can see most the challenge for the EV batteries basically burning because of these materials. But people really enjoy the high energy density. So that's why when I was in the research group, we have a lot of a research grant is focusing on how to improve the NCM materials with much more safety is to control the combustion flame or make it more safer. However, this is still the major challenge for these materials. Little bit more information for the NCM, the ratio you can 1:1:1, the nickel, cobalt, magnesium. But also you can have a high nickel content like a NCM 6:2:2. That means the ratio is 6, 2, and 2. So in the past, we're trying to increase the nickel content as much as we can because higher nickel content show the higher energy density. However, give you more risk with the safety. So that's why we add on a lot of coating, everything. But that is the trend maybe 5 years ago. The new trend right now, people are switching back to NCM like a 622. The mid, we call the mid nickel content, like a not so high but not so low, still with a good energy density, but not that dangerous. So yeah, there's a lot of information about the NCM materials. But let me move on. So NCM materials, this one is also for the electrical vehicles. The difference with NCM, this is a little bit cheaper because the aluminum is a little bit cheaper. And also this one, NCA materials, the ratio has already defined the nickel content is 85%. The cobalt is roughly about a few percent. So that's why it's cheaper than NCM. NCM nickel is right now is 60%. So this material is particularly used by Tesla. So you can see the most of the high performance car using these materials. And next one, LMO right now is not many people using LMO, but the power tools using this stuff. And also the very old Nissan Leaf Jing one using this material as well. Actually, this one is pretty robust, but the problem is energy density. So last, the LCO is one particular for the consumer electronics, and it's good with the energy density, but it's very expensive. All your iPhone, iPad using these materials. So I put how we use these materials here. So this gives you the most important 5 categories for the lithium-ion batteries. And you can see the different materials has a different value to recycle. People focusing on more for nickel and also cobalt, but unfortunately, I'm going to show later on, if you only recycle nickel cobalt, the cost is still very high, and you cannot make it economically reasonable and also very pollution. All right, so after talk about the chemistry, this is talk about one application for electrical vehicles. So in the EV, so if you remove the shell, you can see the whole car actually just much more simpler compared with the gasoline car. So in the middle this is a battery. In the middle, this is a battery, one battery pack. So, but if you open the battery pack, you will see 10 modules. Actually, this is not really each cells, but you have a different section, like a 10 modules. Each module has maybe 150 to 100 cells. The reason why we want to mention this because we want to let you know that more than half of the cost for the EV is the battery, and inside the battery, this is a little bit too small. Inside the battery, more than half of the cost is from cathode active materials, which is nickel, cobalt, magnesium, and lithium. And there's 3 major battery type. One is called a cylindrical cell, which is round, like your normal battery looks like, and the wrap inside and to make it a cylindrical cell. The good thing is this is very safe because you have aluminum or stainless steel case outside, which is very strong, very safe. The challenge is that the energy density is not that so high. And the bottom part is called a pouch cell, which is kind of like a plastic, the outside and the make a 10th layer or 20 layer inside. You put one together. The challenge for this one is that because it's not so hard, no solid shell outside, so the safety is one concern. So this one used to be very popular, but we believe for the future trend, this will be less and less. Prismatic basically is you put all these cathode anode materials inside and electrode inside, and make it like a box. So this can be made from small and very large. This one is majority used by I think majority used by the EV in China and also energy storage system, and most used in the LFP materials. The good thing for this one is the energy density. So that's, we believe, will become the future trend because the energy density is really important, and also safety. Okay, so this is some background for 3 type of the batteries. And okay, so we have this cost breakdown. So you can see the cathode compound in the battery is really the biggest part for the batteries. More than half of the cost is the cathode active materials. And that is, we have a biggest gap in the US in the future. So we can only produce probably less than 1% by 2030. And we even didn't see the chance that we can produce more because we are missing a lot of this kind of the manufacturers. The anode is 12%, which is a graphite, is also important. So how we can get those materials back, that is, as a recycler, what we want to do. So there's a more detailed the breakdown for these materials. Active cathode materials, aluminum, copper, anode, electrolyte, and so on. So this is all the breakdown. As a recycler, we want to get everything back. But eventually, you really need to think about the cost, which one you can make it reasonable, you can bring them back. So right now, I'm going to show our technology later so you can get a more idea. Okay, so after use the batteries, basically battery will become an end of life. So basically, I think for your iPhone, iPad, probably just less than 5 years. EV, we don't know. Looks like EV electric vehicle is much more robust than what we thought. But anyway, so eventually this go to end of life. You want to recycle them and you want to handle them properly because there's toxic stuff inside. You do not want to put them in landfill. Okay, so this is the part we want to show the market for the recycling. So left-hand side, basically, we want to show what need to be recycled now and also in the future. So if you see, let's see this figure first. It's a little bit too small. So the green color is called a manufacturing scrap. So when you make the battery, you're actually making a lot of scrap at the same time because you need to cut something, so you have a lot of manufacturing scrap. Actually, in the battery manufacturing, the scrap ratio is pretty high. You can see the left-hand side, we show the scrap ratio. So basically, it's starting from 10 to 12%, and hopefully, eventually, we can down to like a 5%. But unfortunately, right now, I think the real number is much higher than this. So this is for manufacturing scrap. And the blue color is for end-of-life batteries. So you can see probably before 2030, the manufacturing scrap is the biggest market. And because most of the cars are still on the road, so not need to be recycled, but end-of-life battery will catch up in the future. So this is what we want to show to this. And the bottom part is by geography, different locations, the total volume need to be recycled. The red color is from China market. This is the biggest one. North America is become bigger and bigger. It's light blue, and dark blue is Europe. and the rest of the world is the green color. So just give you the idea, so where's the most waste coming from. So right-hand side is talk about three recycling technology. We actually using this figure from Argonne National Lab. Okay, we put it here. So internal called the direct recycling. And the next one is called a hydro process, and then it's a pyro process. So you can see for the different technology, you're gonna go back to the different stage. The blue color starting from mining, refining, cathode production, battery manufacturing. So this is the stage for the from mining and all the way to make the batteries. So you can see different recycling technology skip the process. Like see, the pyro you have to go back to refining, but hydro you can go to the cathode production, but direct recycling you can go to battery manufacturing. The different is the process and also the product also different. We have more detailed information. So the pyro process is a high temperature. You can see this is how it looks like. And actually should be even worse than this. The hydro process, looks very nice. The hydro process, basically is the acid leaching process. You pour the sulfuric acid to dissolve everything, and you put additional chemicals, you get the metals extracted. So that's why you need a lot of acid. So the last one is called the direct recycling. It's what we're focusing on. So we don't use the hydro, we don't use the pyro. So we basically separate each component and get a cathode powder outside. Don't break them and reuse them using plasma technology. I'm gonna show for the following slides. Okay, so when you have this is the recycling process. Basically, when you have the electric vehicles or energy storage, the end of life, you get a lithium-ion battery pack. You cannot handle pack directly because it's very dangerous. First of all, it's a lot of the power inside. So I remember someone told me, I don't remember exactly, but one battery pack can basically support your entire home for over a week. So that's why you can see a lot of energy inside. You need to discharge first. You do not want to handle them without discharge. And discharge a battery pack is not easy. So this is a one challenge. The other challenge is to disassemble, because you do not want to, the traditional like the vehicle, you're just shredding them just one step, but you cannot shred in a battery pack. It's dangerous and also not efficient. So you want to disassemble them. So after you get each cells, basically each battery cells, and you want to start it from there. And this shows like a consumer electronic just come with a cell. And after that, you basically have a couple of the process. You can continue disassembling. You can also shredding the batteries and doing the separation work. It's like a 5 to 10 steps, we call it pre-process, shredding, separate the component. And basically after that, you go to these 3 different technologies. And this figure, we also got from one of the paper, and to show this is basically the direct recycling has all advantages, but only one thing is you need to sorting the battery, because direct recycling, at the end, you get a cathode powder. You cannot mix all kinds of battery together. You want a single chemistry to have a direct recycling. All right, so, okay. So the traditional way to recycle batteries, you get this waste batteries, you're shredding them, you get like all the cathode is broke. So you have to dissolve them into the liquid or high temperature smelting. Basically, the goal is that you want to get a nickel, cobalt, and magnesium. So basically, this way you get a nickel, cobalt, magnesium all separately. Hopefully clean enough, but this is really challenge, because if you want to get a really clean cobalt and nickel separately, which is not easy. They are so close on the table. So basically, but even this, you have to use a lot of energy, a lot of the waste water and waste gas. I can give you one example. So using sulfuric acid as a dissolve everything, you need to neutralize this acid. At the end, you have a lot of sodium sulfuric. Basically, this waste is already over what we can handle in the entire world. We don't have any place to dump this stuff, and we don't have a process to handle them. So this is just one example. For example, for the metal extraction, you need to put like ammonia gas inside. All kinds of this waste is you have to handle at the end. So that's why in the US, for this traditional recycling technology, it's really difficult to survive. Not only permitting, but all this process waste, the cost is much higher than if you compare if you do outside. It's just very high cost. Okay, so after that, you want to make the new cathode powder to mix them together. Okay, so for direct recycling, we're also facing the same issue, basically the broken cathode powder. But the goal for us is we do not want to separate the nickel, cobalt, magnesium separately, because if you separate them, then you actually waste a lot of energy, because we put a lot of effort to make this cathode powder, and most of them actually still function. Our purpose, what we try to reuse. So the goal is trying to remove all these impurities and then fix the problem with the cathode powder and reuse them. The reason why we can reduce the emissions waste, because we don't break down all this element. We didn't put too much the chemical inside. So that's why the waste is much less than traditional technology. And I want to give, okay, this show we have a trade secret and patents. I want to move on to the next slide. So this gives you the other overview for the direct recycling and the traditional way of recycling. So again, the blue color is you get the cathode active materials, you make the battery, how you use the battery, and then at the end, you collect the battery. You want to recycle the battery. So traditional way, you can see they go through the leaching process, extraction process, you get a sulfate, and the refining process, and then you synthesize new materials, and then make the cathode materials. So each steps is very is not a simple. Each step needs a lot of chemicals and energy. And for direct recycling, we want to skip all of this. We want to put the cathode powder directly regeneration to the new cathode powder. So this gives you very simple chart to see how the direct recycling works. So you shorten the process time, reduce cost for about 40%, reduce a huge amount of emissions. We are very conservative for this number. For example, we didn't consider today the traditional recycling technology, the materials need to ship all over the world, maybe for 50,000 miles for the materials, but we don't need to do this. So that's why if we add on everything like this is a very conservative number to us. And also this is gonna support a local supply chain. This is a more detailed information about our own process, how we recycle the batteries. So from the top to the bottom part is the major step for our process. So like cess reductions, basically shredding everything, remove electrolyte as a first step because you do not want the smell go everywhere. And the component separation, you want to have a copper, aluminum, plastic, and others all separated. And then we can focus on cathode and anode. So this is a byproduct, copper, aluminum, plastic, and some lithium solutions. And after that, you get the anode and the cathode powder only because copper, aluminum already go outside. And you want to separate the cathode and anode materials. Basic anode materials is another byproduct. And the cathode powder continue go inside. Purifications, you get like a smaller impurities out. And then the cathode is more or less clean. And next step is using our low temperature plasma, basically remove all these organic binding materials at the surface of the cathode powder. So some trace impurity will be gone. And then the cathode powder will become pretty clean at this stage. And then the last is the rejuvenation step. Basically, you need to add a lithium because the battery you're using for a long time, you lose lithium. You won't lose nickel cobalt, but you lose lithium. You need to add the lithium back to make it the original capacity. So at the end, the product is a battery-grade cathode materials. Too much information here, I understand, but hopefully give you the step how we do step by step how to recycle batteries, and you can see that we don't have acid involved and no toxic chemicals involved. So that is very important for the recycling process. And these slides we put here is normally I will explain this to my partners or investor. It's a little bit complicated, but still want to give you more information. The top part is for traditional technologies. So most traditional recyclers are focusing in this box: thermal process or acid leaching process, which is pyro or hydro. So you can see like a smelting, leaching, separation, purification. Those words I always say is not a simple, just one word. They are very complicated behind this chemical process. You need a lot of chemicals and a lot of energy behind this. So that's why if you see that today all the recycling company in the US, if they step into this traditional technology, they really difficult to compete in their product price with outside the import price. And after that, you'll go through refining process, synthesize, cathode production, making new materials. So this is a whole basically process from waste to new materials. We give a very conservative time, it's 3 months. So actually, if you consider this is 3 to 4 companies and all over the world, it will take very long time to get these materials back to the supply chain. So for direct recycling, we focusing on a single site. It's all within our plant, so we can do it within like 3 days. So starting from separation, same with the traditional technology, but we separate each component to get a cathode powder outside and use plasma to purify, and then regenerate to get a new cathode powder. So we much more simplify the process and reduce the cost and the emissions. And this work we did together with Argonne National Lab. They have a group called Resale Center. Basically, they have a model to analyze the cost, emissions, energy, and water, and everything. Actually, their model is very complicated. So they show all kinds of chemicals, how much you use, and all kinds of waste, how much you will generate. But we put this a few major stuff: the cost, energy consumption, water consumption, and CO2 emissions, basically to show the difference from virgin, which is mining process, to get new materials, pyro, hydro, and also direct. So obviously, direct recycling has a huge advantage for this process. And also, one example is in our Dallas pilot line. So we are much more, we cannot say it's very easy to get a permit, but much more easier compared with the traditional recycling technology. We get a permit. So that is one thing indicate this is a technology is much more, I would say, you can use in the United States. So this is more like regarding plasma part. So we understand the plasma is a very broad, the range. So we only focus on one part of the plasma. So this is the range of the plasma we use. And there's already a lot of the applications using those kind of plasma. So this is the all kinds of application. So we focusing on is only to remove the organic materials as a surface of cathode powder, but we do not want to damage the cathode powder. So that's the plasma we use. So a lot of people asking us, are you using like a high temperature plasma to melt everything down? I said, no, we are not focused on melt the metals. We just focus on remove all these impurities at the surface of cathode powder. So that is why, think about eating the cathode powder is like a ball, so the impurity is a very thin layer at the surface, like a nanometer thickness. So that's why you do not need a lot of energy to melt down everything. More question, Xiaofang can answer later. So this is our plasma. I would say this is our Gen 1 plasma. So we already have a Gen 4 plasma right now with the entire equipment. So this is Gen 1 plasma. We have what we call a 3-in-1 design. Basically, is you want to carry your powder together with the gas together into your plasma. So it's a gas solid mixing unit, and then it's a plasma unit, which is active the zone that reaction will happen in here. And after that, you have a gas solid separation unit. You want to have your waste and separate together with the gas, and the powder you can collect at the end. So this we pretty high throughput. We cannot say this is super high throughput, but it's a pretty good high throughput. It is sufficient for us. For the materials, the worry is that people don't make like a the giant facility, the single facility, like people, we use like a chemical plant to make the ammonia. It's not that the kind of the process. So people using like 10 lines or 100 lines, each line is like a few hundred tons. So this is how people make materials. So we have a similar concept for our plasma. We do not want to increase our plasma unit to a giant plasma, because we think it's very difficult to control uniformity and many things. So that's why for our each plasma module, we can handle for a few hundred tons. So we will duplicate them to have multiple lines to process the materials. So that's just what we realize is easier to achieve instead of to make a giant one. But this is very complicated. We work on this for a long time. And I'm not sure we have more slides, but we have a Gen 1, it's very small single tube. We have a Gen 2, Gen 3, Gen 4. So Gen 4, basically, we have multiple zones with multiple modules combined together. So it's a fully industrial standard reactor, the equipment. This is more like how it works. So I try to use this one to let people to understand what we're focusing on. So actually, I don't think this is good picture. So basically, this ball is a cathode powder. The purple one is a plasma zone. Basically, we mix with a cathode with a carrier gas into the plasma reactor, and you won't have a reaction happen on the surface. Actually, what we're focusing on is this stuff, this small stuff. This is what we're focusing on, because we know the ballpark we do not want to touch. If you touch, you damage it, then you cannot recover it. So we just want to remove this impurity. So you can see after that, those impurity will be outside, so you get a clean cathode powder. This is very difficult, because if you're people try to using like a high temperature to heat, like a evaporation or like a combustion way. So none of them can do the job. For example, if you heat up, so this waste, this impurity gonna be diffused inside. Instead of go outside, it diffuse inside. And once it diffuse inside, you cannot to process anymore, because heating you need a long time, but plasma is much faster than that. But yeah, so this is how we're using this plasma is a focus on this small stuff. So that's why I said this figure is no good. We should highlight this small stuff. And this is more like one more slide. We show how it works, basically the etching process. So basically how we physical etching process and the chemical etching process to get this impurity out. Okay, so here's some like kind of like end product, how it looks like. So A, B, C. A is the before process, B is after process, C is the impurity. So A, you can see before process, you have a cobalt, which is what we want. You have this is LCO, so that's why only cobalt. But you can see there's a lot of impurity like aluminum, copper, some others. But after you purify, basically you can only have a cobalt. So that's exactly what we want, lithium cobalt oxide. But if you watch the impurity, you can see all kinds of aluminum, copper, it will be in the impurity. So this indicate we successful cleaning the process. So this is just one example. We have done this many times for all kinds of cathode active materials. So yeah, to prove this is very efficient process to clean it. And also, we don't need to worry about damage the cathode powder. Okay, so this is the recycling market. So at the end, the company need to focus on the market. We see that no matter it's a global EV sales, no matter it's faster or slower, the trend is very clear. It's gonna grow, and also the huge demand for the lithium-ion batteries. That means a huge demand for the materials. And then the bottom part is for recycling. The global recycling market gonna grow roughly every year is 20+%, and in the United States, growing even faster. So recycling has a big potential and very important because we don't have a mine in the US. If we just dump this waste, which is we waste really a lot. So we want to collect those waste and reuse and put back into our supply chain. So this is go back to the original slides. So we want to show majority is our the product. So this is original product a few years ago. Small sample, larger sample, even bigger one. Right now is already in the pallet. So the tons level, the materials we produce, so we can give to our customer for the validation. So eventually, this validation process is very long. So for example, we're working with one of the auto OEMs. It's already over 3 years. We're still in the later stage of a validation process, from very small sample, larger sample, the tons level. So it's all behind is our equipment also become larger and larger. So that's give us a lot of challenge. But we learn a lot. I think right now we are much more ready than before to go to the scale up step. At the end, we want to show is that I saw this high school student, so that's why every year we have the high school student, undergrad student, and come to our company for the intern. For the internship, is particularly in the summer. So we have the dedicated fund to support a student. So if you have any student want to learn more, this application using plasma and batteries, we welcome them to apply. So roughly every year we'll have like 6 students can come to our company. Maybe this year can have a little bit more students because we have a new space. Okay, so I think the time is up. Thank you so much for your time.
Microphones are on the way. I know there's a couple questions on Zoom. We'll try to get to everybody. I see hands over here, hands over here, hands over here, hands touching hands. Maybe if you stop in the first shift.
Stop.
Yeah. Okay.
Okay.
No, that way I can read the
Yeah. Some.
where we go.
I've got it right here. Thank you. When are you going public?
Typically, investor ask me these questions. Yeah. So it's I think it's that as a company we focus on the exit way, no matter IPO or merge with other company. So what we want to do is that we want to have one plant, the commercial plant, start operation and start generate revenue and also profit. And that time we will consider public. So if you ask me the time, 2 to 3 years, but maybe always people answer is 2 to 3 years. Hopefully market will become better.
I think this is insider trading. Right there.
So you've discussed that your plasma process removes binders and conductive additives, but as we move to more advanced materials such as carbon nanotubes as our conductive additives, you are removing those completely. Furthermore, for home and stationary storage, we're moving to sodium as it is cheaper and safer. Most cathodes, as I've heard, are like Prussian blue, which is an organic cathode, and your process isn't compatible with that. So what are your attempts or mindset for newer materials?
Yeah, this is a very, very good question. I think it's that when I was a student, I always think about let's focus on to synthesize together newer cathode materials and all kinds of doping inside. And I believe if the materials have a better performance, the company who make the cathode materials, who make a battery, will pick up my technology. But in the reality, after we found the company, I talked to a lot of them. So the change for the new cathode materials is a very long process for them. So they will consider all kinds of things. So if you ask me the trend for the future 5 years, the cathode active materials to change, I actually didn't see any chance that they will change to the completely different cathode active materials. So it will still maintain majority NCM system and also LFP system. But you're right, people trying their effort, for example, sodium batteries. I think that is the one thing people are thinking about. But think about right now, the lithium price is so cheap already. Why they focus on the sodium. So this is why the cathode company or battery company, they put a lot of effort 2 years ago about sodium battery, but not many people mention right now because the lithium is already very cheap. Yeah, so yeah, as a recycling company, we always catch up all kinds of new cathode active materials, and we want to make sure we can recycle all of them in the future. But we don't know what we can recycle all of them or not. But at least we can focus on the majority of the cathode powder we recycle them. So for example, you also mentioned like a carbon and nanotubes you put inside. So this one we have to separate them first with the cathode powder. If you really see the who bring these materials inside, I think the chance probably is not so high. The reason is that I think carbon nanotube is very expensive. So the cost of the battery right now is a very, I would say, important topic. All the cell manufacturer, if you tell them you put something stuff, you can improve like a little performance, but you increase the cost, they probably will say no right now because the cost is the biggest challenge right now. Yeah, hopefully answer your question.
To your right, there's someone right in the front, all the way over.
By making materials into a plasma, makes me think about what I learned about mass spectroscopy in my younger days. Can you tell me how this is different?
Xiaofang, you want to answer this question?
Well, you do.
You have to separate the different
Yeah.
elements out at the end, right?
Okay. Let me answer it. Xiaofang, you can add on. So first of all, we don't separate each element. The cathode powder fly inside, and basically the impurity are outside. You want this impurity out, and then impurity will be separate with the cathode powder, but the element in the cathode powder won't separate it.
Just getting the impurities out so that.
That's right. Exactly. Yeah.
Hey, I don't know where the microphone is. Oh, there it is.
Hello. First, I'd like to thank you. I like that you started with a basic slide. I'm not a high school student, but sometimes when you jump into the middle of heavy science, some of us adults don't understand. I understood what you said, so thank you very much. My question's more from the consumer point is, like what do you do with like batteries and phones and smoke detectors that have precious metals in it? How do we recycle it? I mean, who do we give it to?
Okay. I did a detailed work on this. So at the beginning, I started this company. I'm trying to see who I can work with. So I go to like a Home Depot. I check where is your battery flows. I also ask people in Princeton to handle in the battery. We have a bucket. I said, where the battery gonna go? So okay. So eventually, phone or other batteries. Basically, if you drop in those locations, there's a couple of these organization gonna pick them up, like a Call to Recycle, Earth 911, some others. So they will collect all kind of this stuff together, and then they will do the separation work. They will categorize them into different, like a category, like a phone. Obviously, it's different because more value inside, power tools, and something the rest. And they won't do the recycling by themselves. They will give this to the recyclers, like Wistron, our partner. Wistron will collect the phone's batteries, power tools, batteries. I think I think the majority collect those two type of the stuff, and after they collect this, they will disassemble them. So they will disassemble them with the plastic, everything outside, and then the batteries. And after that, they will handle the battery to us. They originally handled the battery to a company in Europe called Umicore. So they handled them to them before 2021. But at that time, it's COVID come and also overcapacity in Europe. Basically, they reject all the cell from Wistron. They said, we no longer accept your cell, so you have to do by yourself. So that's why after that, Wistron work with us, let us to recycle the battery.
So if I bring my batteries to Home Depot, I can deposit them there?
I think you can do that, yeah. And then eventually someone will pick up, yeah.
Next question is right over here in the aisle. Yep. Should be on. Nope. No.
Hi, so this was a very nice presentation. I appreciate it. It was very good. I had a couple of questions. In the first slide, you mentioned about the different types of batteries, and you mentioned how the more nickel you have in them, the higher the energy density of the battery. So I was just wondering about that. And then a question for afterwards about the more technical phase of the cleaning process. There were two parts, the gas and powder mixing phase, and then the gas and powder separation phase. So I was just wondering as to the role of those.
Yeah,
Thank you.
so first one, the higher nickel with higher energy density is the nickel concentration is high. Basically, the battery basically nickel 4 plus to nickel 3 plus. You have more nickel, so you have more energy. So that is why the higher nickel, higher energy density. But higher nickel is very dangerous, so we did a test by ourselves. And the other question you mentioned, how we mix together, because if you don't mix the gas with powder very well, basically you will find out after you process, some powder you processed, some powder you didn't process. So that's why mixing is very important. So that's why we also have a couple of module. We don't process only one cycle. We process a couple of cycles to make sure all this material is being processed.
Thank you.
Right in the middle.
Hi. There was a paper published in Environmental Science and Technology in the middle of the year stating that on the PJM grid, where we live, the embodied energy of an electric car is actually worse than an internal combustion engine. Well, how much embodied energy does your recycling add? And they were talking about virgin materials, but the embodied energy of an electric car on the PJM grid is higher in carbon.
I want to understand, what is the body energy?
Embodied energy is the energy that goes into the process.
Mm.
Okay, so if you're refining cobalt, for instance.
Yeah. So I think it's this topic. I understand people always mention for the electric vehicles, if you don't recycle them properly, it actually even worse than the combustion car. So so that's why for our analysis at the very beginning, we don't think the traditional recycling process is really, I mean, can be more sustainable to do that, because it really not worth you to dump so much chemicals inside just to get a cobalt. Cobalt is okay, but nickel and also magnesium out. Basically, it's not a gold and silver. I mean, it's a massive amount. So I think I agree with you. That's just a challenge for recycling. So that's why what we think direct recycling can change this situation. I fully agree that if a traditional recycling technology is not really make this EV clean. Think about it. I ask a lot of people, even people who they are building this hydro metallurgical plant in the US. I asked them, do you want to buy a house near your plant? They said no. Yeah.
There's a question over here. Should be on. Nope. Yes.
Hello. Hi. Thank you so much for the talk. I really
you.
appreciate how you started from the basics. It really helped me learn and understand. I was wondering, so I know we're currently in the transition from liquid to solid state batteries, and I was wondering whether your company focuses on like both and how that affects the recycling process?
Yeah. My daughter asked me same question. She's 10 years old. So, yeah, so yesterday, 2 days ago, I do a little rehearsal with her. She asked me some questions. This is one of the questions. So the solid state battery, basically the cathode and anode materials, the cathode materials is same with today's cathode materials. The difference with the electrolyte and anode part. So that's why if you see the business perspective, this is the most important part. We cover this. And the anode part is actually even easier for recycling because there's a couple of the solid state anode. One is like a lithium metal. So if compared with the lithium metal with the graphite, lithium metal is more easier to recycle than graphite. So I don't think the solid state battery will be challenged to us. The more challenge to us if they are changing the cathode active materials. If that question is really good, if that one's changed, and then we have to think about how we can catch up for the new recycling process.
There's a question online. How do impurities get into the lithium in the first place?
How the impurities get to the lithium? So the impurity, so for the cathode, is mixed with the lithium, nickel, cobalt, magnesium. It's a mixture. So the impurity, majority of them will be at the surface. So it is not really sticky with the lithium. It's at the surface. So that's how you basically physically it's outside. You remove them. But actually some impurity will get inside. So the plasma is a good tool to get some of them out. But if you really ask 100%, can we get all of them out? I cannot guarantee, but that is a much more complicated insight. Yeah.
Thank you. Oh. Hold on, just for the people online.
So when we talk about the impurity, it's actually the part of the component in the batteries. For example, the fluorine is actually part of the electrolyte. And we need to have a very clean cathode materials. And that's why we need to remove anything not part of the cathode materials. And the majority is from the electrolyte, for example, the fluorine. So it's not the impurity from outside, like dirty dust. No, it's not. It's actually part of the batteries because they're attached to each other, they're mixed with each other, and we need to remove them in order to achieve the best performance, in order to reduce impedance when they make batteries and facilitate the lithium transportation between anode and cathode. So I just want to be clarified of this part. Thanks.
Right in the middle. Yep.
I have a fundamental question. So when a new battery starts, it has a cycle of, discharging it and charging it again, and eventually it dies. What is basically making it die? What happens at atomic level or at a chemical level that makes it die?
Okay, I think the most reason, there's many reasons, but the majority reason is that the lithium eventually cannot get inside the anode and get outside the anode. Same thing cannot get inside the cathode and get outside the cathode active materials. That's the major reason. But why that happened? So after you form many times, the lithium itself plus electrolyte will react with the surface of the cathode and anode materials. And that blocks the lithium going inside and outside. So that's why you see your energy density will lower. Eventually, you cannot charge in any electricity inside.
And that's what you call the impurity, and that's what you remove. Is that?
That's right.
Okay. Yeah. Thank you.
Right over there. Up, back in the right.
Sure.
No.
Okay, I think we got it. Thank you. Thank you for a really brilliant and understandable lecture. Really, very well done. Thank you.
Thank you.
I have two questions. One, we talk about plasma, and when you were showing the diagram of the different kinds of plasma, I didn't really get a good sense of what temperature your plasma is at, because you differentiate yourself from the pyrotic process. And I'm just trying to understand, like, what kind of temperature does your plasma operate at in order to be able to do the impurity separation? And that's question one. Number two, I want to get an idea of what is the efficacy or the effect of the impurity removal process. The powder you give back, is it at 100% again, or is it at 98%, 97% of what virgin material would be at?
Okay. First question I will answer in general, and if you need more information, Xiaofeng can answer later on. So the plasma, we use low temperature plasma. That is definitely not going to like beyond 2000 degree because we do not want them to damage our cathode active materials. So low temperature plasma. The second question basically, sorry. Yeah. So the second question, the performance, basically, what we can do right now for LCO, which is consumer electronic device battery, and some NCM battery with some auto EM, we can recover to 100%. And some of the high nickel compound, I think we are close to 100%. Yeah. So that is the goal. Yeah.
In the back, in the corner. There you go.
Yes, hello, thank you. Where do the waste products from the recycling process go? I know there's many different kinds of waste products, but are they put in underground storage facilities or where do they end up?
The waste, that's a very good question. So I think today in the US, there's no solid the answer yet because there's no plant yet to recycle. So for us, our waste is the gas waste, we will handle them by ourselves. There's no gas waste to go outside. Basically, we convert them into the solid and we're gonna pay for others to handle them. So the liquid waste, we also very minimize because we don't have acid. So for us, it's just a cleaning waste. So we also pay others to handle them. So that is the waste, majority of waste from us. But for the traditional technology, the waste, the majority is the liquid waste. I think they have to build the waste processing plant to process that waste because that is a massive amount. But eventually, if you get like a sodium sulfate, you still have to sell to someone to handle for you because you don't have anywhere to put them. So this is the waste.
Do you know where those folks put their waste? I mean, is it big tanks somewhere or?
I don't know, to be honest.
Okay.
Yeah, sorry.
One row up right there with the hoodie. Yep.
How much energy does recycling the lithium-ion batteries actually save? Like how much energy does it save?
Oh, wow. I don't have an absolute number right now in my mind, but we can see that compare with the virgin materials, which is from mining process to the new materials, we reduce roughly about 40 to 50%. If we compare with the hydro process, we roughly reduce about 40%. So this is not absolute number, but if you really want, I can get to you. I don't remember right now.
Off to your left.
Hi, thank you for an excellent talk. The government has been investing in a battery plant in Nevada, and I don't know much about it. Maybe you could tell us more. Is it the same kind of lithium technology battery that they're going to plan to build there? And how does that affect your company? And I'll just leave it at that.
It's a recycling plant?
No, this is, I think, production.
Battery production plant in Nevada. I think in Nevada it must be in Reno, so it's in that region. So I know the Department of Energy put the money into one of the company, Redwood Materials, and also ABTC, two companies for recycling. So both of them using traditional recycling technology. And the reason they choose Reno, Nevada, because two reasons. One is very close to Tesla, Panasonic, Gigafactory, so they have a lot of waste. And the second thing is that in that particular location, so the regulation permitting is much easier than like California. So that's the reason they choose that location. But all of them using traditional technology. So how the effect the government grant support them compared with supporting to us? I think it's that overall, the U.S. need a huge amount of the recycling capacity. So I don't believe any of us can do by ourselves, one company or two company. I think at least U.S. need 10 companies to handling the waste. So for sure, if they get a more grant, that's give us more pressure. But I think eventually we need more partners. And in particular, I think all of these companies, if you see they are bigger right now, they're using traditional technology. I think they need a better technology. So eventually, I think they become our partner somehow in the future. But you said the government's supporting maybe into the gigafactory in that region. So if the government support more gigafactory there, which is good for us because more gigafactory, they produce more batteries and they will have much more manufacturing scrap for us to recycle. So it actually increase our market in the future. So that will be good. Yeah.
Right in the front, right for you.
Is there any limit to the number of times the like the cathode active material can be recycled?
The goal for us is can recycle. You can recycle forever, continue to recycle. But in reality, basically you need to see how the battery going to be used for how the customer use the battery. So if you use the battery in a very harsh condition, maybe just one cycle we cannot recycle anymore. Because if cathode power already broke, then there's no cathode power, then you cannot recycle using our technology. You have to go to traditional way to recycle the process. But based on what we observe for the end of life, the electrical vehicles, 80% plus the materials we can continue to recycle.
And with that, can we give one more round of applause for just a really wonderful talk?
Thank you.